When you look up at the night sky, filled with silent points of light scattered across an immense darkness, have you ever asked a question so simple that it almost feels inappropriate to take seriously? If we could gather everything that exists, every star, every galaxy, every particle, every quantum field into a single system, and ask what is its total energy, what answer should we expect? Instinct tells us it must be enormous, overwhelmingly positive, an unimaginable sum built from all the mass and motion we observe. And yet modern physics quietly suggests something far more subtle, that the total may not be large. It may not even be small. It may be exactly zero. This is the moment where intuition begins to fail. Not because the universe is mysterious, but because our everyday reasoning was never designed for complete systems. In daily life, we only ever interact with fragments. We lift objects. We heat them. We accelerate them. And in every case, energy appears as something we add. Something positive. Something that accumulates. So we naturally extend that logic to the entire universe. We imagine a vast inventory of positive contributions. Mass converted to energy. Motion stored in stars. Radiation streaming across space. But this picture is incomplete, because it ignores a contribution that behaves in the opposite way, one that does not add, but subtracts in a precise and unavoidable sense. Let us begin with something simple. A rock resting on the surface of the earth. When you lift it, you perform work. You transfer energy from your body into the system, and the rock gains gravitational potential energy. Now, here is the crucial step. We define the zero of gravitational energy not at the ground, but at infinite separation. When the rock is infinitely far from the earth, and no longer feels its pull. In that state, there is no interaction, and we assign the energy to be zero. But when the rock sits on the ground, it is not at zero. It is in a bound state, and its gravitational energy is negative relative to that reference. This is not a trick of notation. It is a physical statement about work. To move the rock from the ground to infinite distance, you must supply energy. You must overcome the gravitational attraction. That required input is exactly what brings the system from a negative value up to zero. In other words, gravity introduces an energy deficit, a binding that lowers the total energy below the level of complete separation. Now take one step further. Consider a planet orbiting a star. The planet is moving rapidly, so it carries kinetic energy, which is positive. At the same time, it is bound by gravity, which contributes negative energy. When these are added together, the total is not arbitrary. It is constrained by the structure of the orbit. And in stable systems, it settles into a balance, where the sum is small compared to the individual parts. This is not a coincidence. It is a general feature of gravitational systems. Now imagine repeating this structure at every scale. Stars bound in galaxies, galaxies bound in clusters, structure upon structure. Each level adds positive contributions from motion and mass, while simultaneously introducing negative contributions from gravitational binding. The positive terms are visible. They shine. They radiate. They move. But the negative terms are hidden in the structure itself, encoded in how these systems hold together. The more tightly matter is bound, the more negative the gravitational contribution becomes. This is where the work of Isaac Newton enters quietly, not as history, but as structure. In writing down the law of gravitation, he introduced a mathematical expression for energy that carries a negative sign. That sign is not decoration. It encodes the existence of bound states below zero. Long before we understood galaxies or cosmic expansion, this single feature already implied that gravity changes the accounting of energy itself. But Newton's picture still treats space as a passive background, a stage on which matter moves. In the 20th century, this view is replaced by something deeper. In the theory of Albert Einstein, where gravity is no longer a force in space, but a manifestation of space-time curvature. Now energy is not just carried by objects. It is woven into the geometry of the universe itself. The distinction between positive and negative contributions becomes part of space-time structure. So at the end of this first step, we have not proven that the universe sums to zero, but we have removed the assumption that it must be positive. We have seen that even the simplest systems contain both positive and negative contributions, and that these are not optional. They are required by the laws of physics. The idea that the entire universe could balance in the same way is no longer absurd. It is a natural question. In the next step, we will build the concept of energy with precision, define it carefully, and then return to the question. Not as intuition, but as physics. We now proceed with the part that cannot be rushed, because everything depends on it. If we are going to seriously ask whether the universe can sum to zero, we must first understand exactly what physicists mean by energy. Not in a vague everyday sense, but as a precise quantity that can be defined, measured, and conserved. Energy in physics is not a substance. It is not something that flows like a liquid or accumulates like a pile of objects. It is a number assigned to a system, a quantity that remains constant under well-defined conditions. When we say energy is conserved, we do not mean it is stored somewhere physically visible. We mean that when we carefully account for all contributions, the total does not change with time. This idea is so fundamental that it survives every major revolution in physics. From classical mechanics to relativity to quantum theory. Now, let us begin with the most familiar form: kinetic energy. The energy of motion. If an object moves with speed, it carries energy proportional to the square of that speed. This energy is always positive. It increases as motion increases. Then we add another form: potential energy, which depends not on motion, but on configuration. How objects are arranged relative to one another. Here is where gravity enters in a way that changes everything. In most everyday situations, we choose a convenient reference point for potential energy. For example, setting it to zero at the ground. But in gravitational physics, there is a more natural choice. We define zero energy when objects are infinitely far apart, completely separated. No interaction, no binding. This choice is not arbitrary. It reflects a physical condition, a system with no gravitational influence between its parts. Now consider what happens when two masses come closer together. They begin to interact. They accelerate toward each other, and their configuration changes. The remarkable result is this: the potential energy of the system becomes negative. We must slow down here, because this is the point where intuition usually breaks. Negative energy does not mean something unphysical. It does not mean energy is missing. It means that the system is bound, that it would require an input of energy to separate the components back to infinite distance. Think of it this way. Imagine two masses initially at rest very far apart. Their total energy is zero. As they move toward each other under gravity, they gain kinetic energy. They begin to move faster. But energy cannot appear from nowhere. So where does this kinetic energy come from? It comes from the gravitational field itself, whose potential energy decreases, becoming more negative. So we have a balance. Kinetic energy increases, gravitational energy decreases, and the total remains constant. If the system becomes bound, meaning the objects do not escape to infinity, then the total energy must be negative, because you would need to supply positive energy to break the system apart. This leads to an important conclusion. Any gravitationally bound system naturally carries negative total energy. Not just locally, but as a global property of the system. This applies to planets orbiting stars, stars bound in galaxies, galaxies bound in clusters. The deeper the gravitational binding, the more negative the energy becomes. Now we introduce another essential piece. Mass itself is energy. This is the statement of mass-energy equivalence. Every particle carries an intrinsic positive energy simply by existing. Even if it is not moving, even if it is not interacting, its mass corresponds to a large positive energy. So now we have two competing contributions. Positive energy from mass, negative energy from gravitational binding. And the question becomes precise. When we add these together for a large system, what is the result? In small systems, the positive term dominates. The rest, energy of mass, is enormous compared to the gravitational binding energy. But as systems grow larger, as more mass is brought together, the gravitational contribution increases faster than intuition suggests. Because gravity is cumulative, every piece of mass interacts with every other piece. This is the key idea. Gravity is not local. It is global. It connects every part of a system to every other part. And because of this, the total negative energy can grow large enough, in principle, to balance the total positive energy. At this stage, we must be precise and cautious. We are not claiming that this balance must occur. We are showing that the laws of physics allow it. There is no rule that forbids the total from being zero, once gravitational energy is included. Now we take one more conceptual step. Energy is always defined relative to a reference. And in gravitational physics, that reference is typically chosen at infinite separation. But when we consider the entire universe, there is no external reference point. Nothing outside the system. This makes the question of total energy more subtle, and pushes us beyond Newtonian physics into a deeper framework. Because if the universe is all that exists, then its energy cannot be defined by comparison to something outside it. the accounting must be internal, self-contained, and governed by the structure of spacetime itself. This is where the next step becomes unavoidable. Newton gave us the language of forces and potentials. But to understand the energy of the entire universe, we must move to a theory where space and time are not passive, but dynamic, where gravity is not a force but geometry. And so the question evolves, not just what is the energy of the universe, but how is energy defined when space-time itself can bend, stretch, and evolve. In the next step, we will follow this path, from Newton's equations into the geometry of general relativity, and we will see that the idea of a zero-energy universe is not just allowed, but emerges naturally from the deepest structure of the theory. We now arrive at the point where intuition must give way to structure. Because if the idea of a zero-energy universe is to carry any meaning, it must emerge directly from the equations of physics rather than from analogy or metaphor. Let us begin with the framework of Isaac Newton, where gravity is described as an interaction between masses and where the potential energy of that interaction decreases as the distance between objects becomes smaller. This single feature is not cosmetic. It tells us that when masses come together, the total energy of the system drops below the reference value, defined at infinite separation, which means the system becomes bound and requires energy input to be separated again. Now consider a planet orbiting a star. It carries kinetic energy because it is moving, and gravitational energy because it is bound. And when these are combined, the total energy is negative, not by choice but by necessity. This is not an isolated example but a general result. Gravitationally bound systems, governed by inverse square forces, naturally settle into configurations where kinetic and potential energy are linked in such a way that the total remains negative. Now extend this reasoning to larger systems. Galaxies composed of billions of stars, clusters composed of galaxies, and ultimately the entire cosmic web. In each case, every mass interacts with every other mass, contributing to a network of gravitational binding energy that is both extensive and negative. At the same time, each component carries positive energy through its mass and motion. So the total energy of the system becomes the result of a competition between large positive and large negative contributions. The important point is that gravity is cumulative. It connects all parts of the system globally rather than locally, which allows the negative contribution to grow in magnitude as the system becomes larger and more tightly bound. At this stage, the Newtonian picture has taken us as far as it can, because it assumes that space is a fixed background in which energy can be defined globally without ambiguity. But this assumption breaks down when we attempt to apply it to the entire universe, since the universe is not embedded in anything larger. It is the totality of space itself. To proceed, we must move to the framework of general relativity developed by Albert Einstein, where gravity is no longer a force but a manifestation of space-time curvature. In this theory, mass and energy determine the geometry of space-time, and that geometry determines the motion of matter. So energy is no longer something that exists independently of space, but is intertwined with the structure of space-time itself. Now we encounter a subtle but essential issue. In general relativity, energy can be defined locally but not always globally in a unique way, because the curvature of space-time removes the possibility of defining a single universal frame of reference. This means that the question of total energy for the entire universe is not as straightforward as in classical physics. And yet in highly symmetric cosmological models where the universe is homogeneous and isotropic, we can still extract meaningful global behavior. In these models, the equations indicate that the positive energy of matter and radiation can be balanced by the negative contribution associated with gravitational curvature. This is not imposed externally. It arises from the structure of Einstein's equations themselves, where expansion, geometry, and energy content are inseparably linked. So, we reach a critical conclusion. The idea that the universe may sum to zero is not a speculative add-on. It is a possibility embedded within the mathematical framework of gravity. However, we must remain precise. This is not a proof that the universe is exactly zero, but a demonstration that such a balance is consistent with our best physical theories. The next step is to confront this idea with observation, to examine the large-scale structure and geometry of the universe itself, and determine whether reality supports this delicate cancellation between positive and negative energy. We now leave the safety of pure theory and step into the domain where physics is forced to confront reality, because it is one thing to show that a zero-energy universe is mathematically allowed. It is another to ask whether the universe we actually inhabit behaves in a way that makes such a balance plausible. The question is no longer abstract. It becomes empirical. What does the large-scale structure of the universe tell us about its total energy? To answer this, we must focus on a property that at first seems purely geometric: the curvature of space itself. In the framework of general relativity developed by Albert Einstein, geometry is not a passive background. It is a dynamical quantity determined by the energy content of the universe. Matter and energy tell space-time how to curve, and the curvature of space-time tells matter how to move. This relationship is not metaphorical. It is encoded directly in the field equations themselves. Now consider three possible shapes for the universe on the largest scales. The first is positively curved, like the surface of a sphere. In such a universe, space eventually closes in on itself, parallel lines converge, and the total geometry is finite even without boundaries. The second possibility is negatively curved, like a saddle, where space expands outward, parallel lines diverge, and the geometry is open and infinite. The third possibility is flat, where Euclidean geometry holds on large scales. Parallel lines remain parallel, and the structure is balanced precisely between collapse and expansion. This classification is not aesthetic. It is directly tied to energy density. In cosmology, there exists a special value known as the critical density. If the total energy density of the universe exceeds this value, gravity dominates, and the universe curves inward. If the density is below this threshold, expansion dominates, and the universe curves outward. But if the density is exactly equal to the critical value, something remarkable happens. The geometry becomes flat. Pause here, because this is the bridge between geometry and energy. A flat universe is not merely a statement about shape. It is a statement about balance. It indicates that the total contributions to the cosmic energy budget are arranged in such a way that expansion neither collapses inward nor accelerates outward due to curvature alone. Now, the question becomes precise. What is the geometry of our universe? This is not speculation. It is something we can measure. By observing the oldest light in existence, The cosmic microwave background radiation is the afterglow of the early universe, a relic from a time when the universe was hot, dense, and nearly uniform. By studying tiny fluctuations in this radiation, we can infer the large-scale curvature of spacetime. This is precisely what missions like WMAP and later Planck have done. They measured the angular distribution of temperature fluctuations across the sky with extraordinary precision. And from this data they extracted one of the most important results in modern cosmology. The universe is remarkably close to flat. Not approximately curved, not strongly open or closed, but flat to within a very small margin of error. This result carries enormous implications, because it suggests that the total energy density of the universe is extremely close to the critical value. Now we must interpret this carefully. Flatness does not automatically prove that the total energy is exactly zero, because in general relativity, global energy is subtle. But it strongly supports the idea that the positive contributions from matter and radiation are balanced by negative contributions associated with gravity and spacetime curvature. At this point, we introduce a concept that has become central to modern cosmology. The idea that the universe may be a self-contained system whose total energy budget balances without the need for external input. This idea is often associated with the work of Alan Guth and the theory of cosmic inflation. Inflation proposes that in the earliest moments after the Big Bang, the universe underwent a phase of extremely rapid expansion, driven by a form of energy associated with a scalar field. During this process, space itself expanded exponentially, and quantum fluctuations were stretched to cosmic scales, seeding the structure we observe today. But here is the subtle point. Inflation does not simply stretch existing matter. It allows for the effective creation of energy in the form of matter and radiation. This seems to violate conservation laws. Until we remember the full accounting, every increase in positive energy can be accompanied by a corresponding increase in negative gravitational energy. So the total remains balanced. Not because nothing changes, but because positive and negative contributions grow together. The universe can expand, create structure, generate complexity, while maintaining a global balance that does not require net energy input. This leads to one of the most striking ideas in modern physics, sometimes described informally as the universe being a free lunch. Not in the sense that it violates physical laws, but in the sense that the laws themselves permit a universe whose total energy is zero. Now we must be precise again. This does not mean the universe emerged from literal nothing in a naive sense. It means that within the framework of quantum fields and curved spacetime, the boundary between something and nothing becomes subtle, because the vacuum itself is not empty. It is a dynamical system capable of fluctuations and structure. So, when we say the universe may sum to zero, we are not dismissing its existence. We are describing the balance of its components. Positive energy stored in matter, radiation, and fields, balanced by negative energy associated with gravity and geometry. At this stage, the picture becomes coherent. The mathematics allows the balance. The structure of gravitational systems supports it, and the observed geometry of the universe is consistent with it. But coherence is not certainty, and this is where intellectual honesty becomes essential. The concept of total energy in general relativity remains subtle, and different definitions can lead to different interpretations. Moreover, components such as dark energy complicate the picture further. Dark energy, which appears to drive the accelerated expansion of the universe, introduces a positive energy density that does not dilute as space expands. This raises new questions about how the balance is maintained, and whether the simple picture of exact cancellation remains valid in detail. And yet, despite these complications, the central idea remains compelling. The universe does not appear to require an excess of energy to exist. It may be structured in such a way that its total is balanced at the deepest level. So we arrive at a remarkable position. We began with an intuition that everything must add up to something large. We followed the logic of physics through gravity, relativity, and cosmology, and we arrived at the possibility that the total may instead be zero. Not because the universe is empty, but because it is balanced. Not because nothing exists, but because what exists is arranged in a precise and constrained way. And now, having traced this idea from simple systems to the structure of the cosmos itself, we are ready to return to the most difficult question of all. If the universe truly balances to zero, what does that mean for the reality we experience? We now return to the question we have been building toward from the beginning. Not a mystical question, but a precise one. If the universe can be described as a system where positive energy from matter and radiation is balanced by negative energy from gravity, what does that actually mean for the reality you experience right now? At first, this feels contradictory, because everything around you appears undeniably real. You feel mass. You see light. You measure energy in every interaction. The ground resists your motion. Your body has inertia. The world is structured and dynamic. Nothing about this resembles absence. Nothing suggests cancellation. But we must be exact about what zero means in physics. It does not mean that nothing exists. It means that when all contributions are included, the total balances. This is a global statement about the system as a whole, not a denial of local structure. A system can contain enormous amounts of energy in different forms: motion, heat, radiation, mass, and still sum to zero if opposing contributions are present. You already understand this pattern in simpler cases. A system with equal positive and negative charges has zero net charge, yet it still produces fields, interactions, and structure. Zero does not mean empty. It means balanced. Now apply this to the universe. Every star that shines, every galaxy that rotates, every particle that exists carries positive energy through mass and motion. But each of these is embedded in a gravitational structure that contributes negative energy. The two are not independent. They are inseparable parts of the same system. The universe is not a collection of isolated objects. It is a network of relationships. Bring this even closer. Consider your own body. Every atom within you carries rest energy associated with its mass. Those atoms are bound into molecules, molecules into structures, structures into a living system. And at every level, binding energy appears. modifying the total, often lowering it relative to separated components. The energy of the system is not simply the sum of its parts. It includes the energy of their interactions. This is the key shift in perspective. Reality is not built from independent pieces. It is built from relationships. Energy is not just what things have. It is how things are arranged and how they interact across space and time. So when we say the universe may sum to zero, we are not describing absence. We are describing a complete accounting. A situation in which every positive contribution is matched by a negative counterpart. This does not reduce the richness of the universe. It reveals the constraint under which that richness exists. At this point, we must remain precise, because this idea is powerful but not absolute. The statement that the universe equals zero is not a proven theorem. It is a consistent possibility within the framework of modern physics. It depends on how energy is defined in curved spacetime, on the role of dark energy, and on the global structure of the universe itself. But even as a possibility, it changes how we think, because it replaces the naive idea that existence requires a net positive quantity, with a deeper idea that existence may arise from balance. Not an excess, but an equilibrium. Not a violation of laws, but a direct consequence of them. So we return to the original question. What does it mean for the universe to equal zero? It means that what we call reality is not defined by how much there is, but by how it is structured. It means that the vast complexity of the cosmos may exist within a framework that is perfectly balanced at the deepest level. As Richard Feynman emphasized in his own way, understanding nature does not remove its beauty. It reveals a deeper and more precise form of it. And here, that beauty lies not in excess, but in exactness. So the next time you look at the night sky, do not ask only how much exists. Ask how it is balanced. Because within that balance, within that exact and unforgiving accounting, lies one of the most profound insights physics offers. Thank you for following this reasoning to its end. Not because the answer is final, but because the question itself reveals how deeply structured the universe truly is.